Hi, my name is Doug, coming to you from Emerald Hill Skies on the outskirts of Louisville, Kentucky. Welcome to another Emerald Hill Skies Skylet. In these Skylets, we talk more about some issue related to the craft of astronomy, and not just astronomy in general, but specifically electronically assisted astronomy, the techniques that we use here at Emerald Hill Skies. If you've seen our other videos or other live streams, you know that most of the time we're just doing practical observing. We're hopping from one object to another, maybe chasing through the Messier list, the Caldwell list, Stephen James O'Meara's Secret Deep, maybe we're going through the Herschel 400, or most recently Phil Harrington's Cosmic Challenge list. But tonight we're not going through a list. We're looking to try to talk about more of a view of a technique or something about the craft of astronomy. I thought tonight we would just start out by looking here at the screen in Stellarium, and I wanted to mention here, this is a photorealistic horizon. You can see this little atrium office building here on the Emerald Hills property where I'm observing from tonight, and the vantage point we have is kind of like the vantage point the telescope would have. And the telescope's looking over the top of the office where I'm sitting. I'm about 200 feet from the observatory. You've probably seen the observatory before. It's a little roll-off roof Tele-Station 2, a Pier-Tech Tele-Station 2, and we use a RASA 11 on top of an iOptron CEM70G mount. On the business end of that RASA 11, there's a camera, the ZWO ASI2600, and it's acting as our eyepiece. So we're both able to see the same thing in a moment when we look through that camera live. Right now we're looking at sort of like a planetarium package to kind of let us see the night sky. If we were to look at it maybe in a planetarium, you can see this part of the sky that we're pointed at here where our crosshairs are. There's a very star-rich part of the Milky Way. You can see it's almost cloudy with so many stars. And we're pointed at a tiny little 50 arc second, very tiny planetary nebula. And if you have studied planetary nebulae before, you know that it's a case where a central star has jettisoned off some of its dying breath of gases, but then it collapses and keeps on burning. As it gets rid of those gases and jettisons them out, it stays alive, and that creates some gravitational and polarity issues that cause those gases to almost become polarized, like a North Pole and South Pole would do in a magnet reaction of the shavings that you sometimes see in the metal shavings. So we're looking for this butterfly nebula, but this red rectangle right here is our field of view. You can see that's going to be a very small target in the middle of our view. And sure enough, when we go to the live view, we're not seeing a whole lot. Now, one of the reasons for that is, in addition to the fact that we're in the middle of the Milky Way, we're only about, let's find the moon. Let's see, there's the moon at 96% luminosity. And let's use our little tool here to measure the angular distance of the sky from this planetary nebula, NGC 2346, to the moon tonight is just about 33 degrees. So I don't know, maybe most people I think would say that if something is within 20 degrees of the moon, it's like virtually impossible. 10 degrees, don't even think about it, it's so bright when the moon is at 96%. And of course the moon's right over the top of it, and obviously it's technically always going to be impossible. Well, the moon is 33% from this little 50 arc second deal. But using the techniques of electronically assisted astronomy, let's give it a try. First thing we'll do here is put our name up here in SharpCap, the imaging program we're using. and it's NGC 2346. NG3 2346. And then we'll change our, maybe our exposure to about 20 seconds and put our gain on about 100. And then we'll start live stacking. Now, live stacking, if you've done electronically assisted astronomy with us before, that's a technique in which you take multiple exposures of a particular night sky object and you overlay them over the top of one another. And in particular, you're not really combining them as much as you're averaging them. And as the software, which is incredibly sophisticated, Robin Glover, the developer of SharpCap, must be a genius, as it's overlaying these exposures, whenever it detects a point of light that's steady, it builds that point of light. But if it detects points of light that are glistening and twinkling and like granular sawdust shavings in a wood shop when the wind blows through it, SharpCap knows that those are not the things you're wanting to observe, and it lets those fade into the black. And as each exposure combines, it gradually gets better and better. So what we do here, we click the display histogram reset button, and then we click the reset of the live histogram down here at the bottom, and we do a color balance, and that tries to make sense out of these color peaks. Then we establish what is a new black level, and it's kind of like defining black for the software. And obviously there's so much moonlight in the screen right now that it would obliterate this planetary nebula, but we're going to pull that black level up until it's right even with the peaks of the colors in this scene. And what that does is it kind of drops out all the noise in this frame that would otherwise be moonlight and also city light pollution. Here on the outskirts of Louisville, we're in about a Bortle 6 sky. We use a light pollution filter by Celestron on the end of that RASA. But still, the sky is just glowing, with city light pollution. And the moonlight is even worse. So we define a new black, and then we also, after there have been 2 minutes and 40 seconds now, we bring our mids down so that it actually begins illuminating anything in the frame that's different than the starlight. And we don't want to get our mids so close that we turn the whole image like moonlit again. But I think you can already see right here in the middle of the frame, there's something that looks different. And when we use our optical zoom to zoom in, now we're at 100% of the optical zoom, you can already see some nebulosity around this star. And look how it looks different than all the other stars in the scene. This particular star has nebulosity around it, and that nebulosity is this planetary nebula. And the longer we look at it, especially on a dark night, we would see more and more color, more and more of this gaseous stuff that's spewing out from the central star. But what makes this planetary nebula, NGC 2346, a little bit different than most is that the central star is so crazy bright. I mean, if you've looked at some of the other famous planetary nebulae in the sky, sometimes you have to really strain to see that central star. Not in NGC 2346. It is so bright that when we were just looking at 3-second exposures, the star showed up, but the nebulosity didn't. And if we want to use the deep sky image annotation, it'll show us, yeah, you're looking at NGC 2346 right there, almost exactly where our star is showing up. So it's pretty accurate deep sky image annotation. We're going to bring these mids a little bit more, and now let's go into some of the digital zoom capability of this camera. And now we're at 150, 100, and now we're at 200%. And we're not seeing a ton of mosaic pixelating yet. We're still just looking at the structure of this planetary nebula. But I want to draw your attention to something. Some people with really good eyes can now start to say that they're seeing a little bit of reds here on the ends, but they're also able to see a little bit of bulge out the sides of this. And I think this is just 5 minutes on a moonlit night when the moon is 96%. But on a darker night, now there we're getting some pixelation, so we'll back off. This is 200%. On a darker night, these poles would show up even more where the star is jettisoning out material against the polarity. And that would be, of course, gaseous particles that have been ionized against this pole electronic gravitational polarity that's produced by the star and its spinning and all, its gravitational axis. So these are being thrown out against. Now again, my color perception's not great, but even I can already begin to see a little bit of red here and a little bit of red there. And that's probably indicative of hydrogen. And then you're probably also seeing some greenish here. And the greenish is indicative of oxygen gases that are being thrown out, typically. This entire width, to put things in perspective, is only 1/2 of an arc minute. And if you're familiar with the way degrees work, there are 180 degrees that we see on our half of the night sky, and we look up in the night sky. It's 180 degrees. One sliver of that 180 degree view would be 1 degree. And then within that 1 degree, you divide that 1 degree into 60 parts, and that's an arc minute. And then you cut that in half, and you have 50 arc seconds-ish. There'd be 60 arc seconds in each arc minute. So a little bit less than an arc minute, between a half and 1 arc minute, is how wide this is. Extremely tiny little object. And with this 11-inch, with this camera, we're able to bring out some of the detail. 7 minutes here is about all we'll see. I think I'm going to take a picture of this, and I'll use a real close-up like this, just because if I were to back off, it would be so tiny. It would just look like a star. And we'll name this in our Sharp Cap images folder here. Sharp Cap captures. We'll name this NGC 2346 dash, and then we'll put 8 minutes dash 24 frames on 2023 dash 11 dash 29, and save that. And that'll be a nice little close-up view we can put into our observing software for the future. So this is one of Stephen James O'Meara's secret deep lists. It's number 34 on his list, and he writes up a nice little write-up on this object. Of course, with a regular visual telescope, you wouldn't see much of this color, if any. And so his actual his picture here that he's using is, just a black and white plate frame. It's pretty much exactly what we were seeing there. This is an astrophoto, and the person might have spent, an hour with a large scope. By large, we mean could have been something like, I don't know, an 18-inch or who knows what. But It's a very faint nebula. It's just 10th magnitude. And he talks about this, you know, polarity that crosses across it. But boy, it's really a treat to see how bright that central star is. And I've been enjoying going through this secret deep list that O'Meara writes about. It's 109 objects, and let me just see here where we are. I think we have wow. Is this the last one? This is the last one on the list for us. So when we add this observation, it will complete the entire secret deep list. That's fun. So we'll say we could make out the reds, the greens, and even some east-west lobe nebulosity, even though this object is tiny in our RASA 11 field of view, 55 arc seconds. And boy, now you can see those lobes a little closer. Wow, so you saw it right here on live TV, the entire secret deep list now observed here on Emerald Hill Skies. You can go back and look at the videos of the secret deep lists and you'll see it all. I'm going to zoom in on this just a little more so that we can make out these east-west poles. I know it's going to turn to some pixelation, but I'm just now helping us see the structure. Look at the structure across this direction, shooting out from the sides, and look at the structure north-south still that you can, or you can't because you're looking at me. Look at the structure that you can see east-west, and then the structure you can see north-south, even though it's starting to pixelate quite a bit there. We'll dial up these mids a little more and see if we can't make that pop a little better. It does start to get grainy from that moonlight. But to just be 30 degrees from a 96% moon, it really does show off, I think more than anything else, the abilities of SharpCap and the whole technique of Electronically-assisted Astronomy, EAA. So hopefully in these few short minutes, you've been able to pick up kind of the technique. Typically, we're on a certain object for around 7 minutes usually when we're not really zeroing in and making a big deal about it. But in 7 minutes, you can pretty much see, I think, almost any of these objects that you can find in the night sky, thousands of them. As long as you're willing to work on some of these skills a little bit. It takes a little bit of practice, but I'm not at this for more than just a year or two, so I think you can learn it as well, and I hope you will. EAA, Electronically-assisted Astronomy, from here at Emerald Hill Skies. Thanks for being a part of this, and we hope you'll stop back by and check out the other videos, and hope you'll hit subscribe if you like this kind of content. Maybe click that bell so that you'll be notified when we do these kinds of live streams. And if you want, if you do like content like this, maybe hit that thumbs up. That gets it up in the heads up searches of other searchers as they are looking for astronomy of note, and it would help us a lot. It doesn't cost you anything on your end. So thanks for being a part of this big deal, finishing that entire catalog of objects from Stephen James O'Meara, The Secret Deep. God bless, have a good night, and most of all, thanks to God for making this beautiful object that we can see. Take care, good night, and God bless.